If you're a building professional in India, you know the name IS 1893. It's not just another document, it's the absolute rule book for seismic safety. It's what tells us how to design our buildings so they can stand a fighting chance against one of nature's most destructive forces. Today, we're not just skimming the surface, we are diving deep into this code, into its core logic, its critical math, and the rules you absolutely cannot ignore. So let's just ask the big question right up front. When the ground starts to shake violently, what's the real difference between a building that stands and protects people and one that becomes a death trap? And look, the answer is never, ever luck. It's engineering. It's about having a deep, practical understanding of, and correctly applying, the principles in our seismic code. This standard, right here, is what draws the line between resilience and ruin. All right, here's how we're going to break this down. First, we'll look at the goal of the standard and its core philosophy, the why behind all the rules. Then we'll get into the practical stuff, mapping seismic risk and actually calculating the forces. After that, we'll cover some absolutely critical rules about the shape of buildings. And finally, we'll wrap it all up with the key takeaways you can use on your projects. Okay, first things first, let's talk about the standard itself. And, the most important thing to get is that IS 1893 isn't some ancient text carved in stone. It's a living document. It has been shaped and sharpened over the years by new research and, tragically, by the hard lessons learned from real earthquakes right here in India and all over the world. You can really see how our understanding has grown just by looking at its history. Each revision was a step up. Back in '75, we got importance factors. The idea that a hospital is more important to save than a warehouse. That makes sense, right? But wow, that fifth revision in 2002, that was a total game changer, heavily influenced by what we learned from the Bhuj earthquake. It really changed how we think about seismic design in India. So what actually changed in 2002? Well, a lot. The seismic map was totally redrawn, for one. They got rid of Zone I because, let's be honest, no part of India is completely safe from earthquakes. But the real headliners, the two things that changed everything for designers were, one, specifying different rules for 3 different soil types. Finally recognizing that building on rock is not the same as building on soft soil. And 2, introducing the response reduction factor, or R. This was a huge deal because it finally put a number on a building's ductility, a concept we're about to dive into. Okay, so this leads us perfectly into the why behind the code. See, if you don't get the philosophy, you can't apply the rules right. IS 1893 is not about creating earthquake-proof buildings. That's just not realistic or affordable. It's about managing risk. It's about designing a building to perform in a very specific, predictable way when an earthquake hits. This quote right here from the code, this says everything. It's a 2-level approach. Level 1, for a minor, more common earthquake, the building should be fine, no structural damage. Level 2, for a rare, massive earthquake, the building is allowed to get seriously damaged. It might even need to be torn down later, but it cannot collapse. Everyone must be able to get out safely. That's the deal. Life safety is the bottom line. So that first level is what we call the Design Basic Earthquake, or DBE. Just think of this as the moderate shakeup, the kind of thing that has a decent chance of happening while the building is still standing. Under a DBE, the goal is damage control. Sure, you might get some cracks, but they should be repairable. The building's core should be sound. Then you've got the big one, the Maximum Considered Earthquake, or MCE. This is the worst-case scenario the code plans for. And here, the mission changes completely. We accept that there's going to be major damage. The building might be an economic write-off. But it has one job: stay standing long enough for everyone to get out. This is the ultimate life safety test. So you might be asking, how does a building survive an MCE when the forces are way beyond what it's designed for? The magic word is ductility. It's a brilliant concept. Ductility is just a building's ability to bend and deform without snapping. It's just like a paperclip, right? You can bend it back and forth a bunch of times before it breaks. In a building, we create this effect on purpose through smart reinforcement detailing, allowing parts of the structure to yield in a controlled way. They soak up the earthquake's energy like a shock absorber, protecting the rest of the building from a catastrophic collapse. All right, so we've got the philosophy down. Now let's get practical. How do we actually start designing? Well, step 1 is always figuring out the risk at your specific location. And IS 1893 helps us do that by splitting the country up into different seismic zones. As of the latest version, India is split into 4 zones. from the low-risk Zone 2 all the way up to the very severe Zone 5. Each zone gets a zone factor, Z. This number basically represents how hard the ground is expected to shake in the worst-case earthquake. So a Z of 0.36 in Zone V means the ground can kick sideways with 36% of the force of gravity. That's a serious number, and it's the foundation for everything that comes next.
Okay, we know our zone, now what? Now we have to turn that hazard level into an actual force, a number in kilonewtons that we can design our building to resist. The main way we do this is by calculating what's called the design seismic base shear. It's the total horizontal push the earthquake gives the building at its base.
And this is the main formula. At first glance, it looks easy, right? V sub B equals A sub H times W. W is just the seismic weight of your building. Pretty easy to calculate. The real magic, the real engineering, is all packed into calculating that little coefficient A sub H. That one value contains the entire design philosophy we just talked about.
So how do we get A? The code gives us this formula, and it's like a recipe. Let's walk through it. You take your zone factor Z, and you divide it by 2. Now that's super important. It's how we scale down from that worst-case MCE to the more common DBE for our design. Then you multiply by I, the importance factor, divide by R, the response reduction factor, and finally multiply by SA over G, the spectral acceleration. Let's look at each of those pieces.
First up, the importance factor, I. This is just common sense, really. A hospital or a school is way more critical after an earthquake than a warehouse, right? Of course. So the code says we have to design them to be 50% stronger, using a factor of 1.5. It's a simple multiplier, a built-in safety cushion for the buildings we need the most. Next up is R, the response reduction factor. And this, right here, is where good design really pays off. R is all about ductility. A really well-detailed ductile structure, like a special moment-resisting frame, or SMRF, gets a high R factor of 5. A less ductile, ordinary frame only gets an R of 3. What that means is the better, more ductile building can be designed for a much lower force. But here's the warning. If you design for R equals 5, but don't actually build it with that special detailing, you're not doing good engineering. You're building a trap. And finally, we've got SAW over G. This is the factor that connects the earthquake to your specific building. It basically looks at 2 things: how wiggly your building is, its natural period, and what kind of soil it's sitting on. The code has these charts that show how forces can get massively amplified if you have a flexible building on soft, jelly-like soil. It's a recipe for disaster, and this factor makes sure you account for it. Okay, doing the math is one thing, but honestly, it's only half the story. The code puts a massive, massive emphasis on the building's shape and its layout. Because a good seismic design isn't just about strength. It's about having a simple, predictable shape that gives earthquake forces a clear path to follow down into the ground. The code basically puts buildings into 2 buckets, regular and irregular. Regular buildings are great. They're simple, symmetrical, and they behave predictably when the ground shakes. Irregular buildings, well, they're the complicated ones. L-shapes, big gaps, sudden changes in stiffness. These create weak spots and twisting forces. They're way, way more likely to get into trouble during an earthquake. And out of all those types of irregularities, there is one that is a notorious killer. It's a problem we see in buildings all over the country. And that is the soft story. The code gets very specific with numbers, but you know exactly what this looks like. It's the apartment building with an open ground floor for parking. You have all these heavy, stiff floors with brick walls sitting on top of a single floor with nothing but skinny columns. When an earthquake hits, that entire building tries to move as one block, and all of that energy gets concentrated on that one weak, flexible ground floor. It's a classic and incredibly dangerous failure mode. Because this is so deadly, the code is absolutely brutal about it, as it should be. Clause 7.10 says that if you absolutely must design a soft story, you have to make the columns and beams on that floor strong enough to handle 2.5 times the earthquake forces you calculated. It's the code's way of saying either get rid of this dangerous feature or make it unbelievably strong. All right, that was a lot to take in. We've gone from philosophy all the way to specific formulas. So let's wrap this up by boiling it all down to the absolute must-knows for any professional using IS 1893 on a real site. Think of this as your mental checklist. First, get your seismic zone right. Everything starts there. Classify the building's importance to apply the correct safety factor. Understand the system you're using and what its R value implies about ductility. Calculate your weight accurately. Hunt down any and all irregularities in the design, especially soft stories. And finally, and I'm going to say it one more time because it's that important, make sure the ductile detailing you designed actually gets built on site. Paper safety doesn't save lives.
And that's where I want to leave you. It is so important to remember that IS 1893, just like any building code, is the minimum legal standard. It's the starting line, not the finish line. For us, as the professionals entrusted with keeping people safe, the real question isn't just, did my design meet the code? The real question is, how can I go beyond the minimum to build something that's not just compliant, but truly safe and resilient? That's something to think about on your next project.